Okay, so P15.4, the motor effect, and this is where physics starts to get a little bit hard. Okay, so last lesson we discussed the fact that if you have a magnetic field, you'd get the current would always be at right angles to that magnetic field. Well, what I'm going to tell you today is that there's another right angle as well. Okay, so for example, we know from our right hand grip rule that if I've got a magnetic field going in this direction, or if I've got the current going in these directions, then let's go with magnetic field in this direction. Then you'll already be able to tell me that my current is going in this direction. Okay, so you already know that's what we've done so far, and that those two are at right angles. That's what we did last lesson. But just like on a graph where you can have x, y, and z, where you've got three lines on a graph at right angles to each other, here you've got three parts of physics characteristics that are also at right angles to each other, and they are magnetic field and current. And then the third one, well, the best way to describe the third one is by showing you the experiment that discovered it. So if you've got a magnet where that's my south pole, that's my north pole, and if you remember from what I very first told you on the very first lesson on magnetism, that the magnetic field flows from north to south. Okay, so that's this one. If I put a wire into this and I have the current, so if you look here, that's the current going that way, so I'm going to do the current going, so I'm drawing a wire going through here like this. Okay, so that would be like having a piece of wire go in between two bits of two poles in a magnet. Quite often you can use a horseshoe magnet to demonstrate this. So that's my horseshoe magnet. This would be my north pole, this would be my south pole, and then you drop a piece of wire in between the two. Okay, and the current is going to be going this way. Okay, because that's that. So these two lines here, they're at right angles to each other. Now something's going to happen in the upwards direction. This is your third right angle, and what's going to happen is that the wire is going to go upwards. Okay, so this one is motion, and this one is known as Fleming's left hand rule, and I'll show you why in a second. And that's basically, if you take your left hand, it has to be your left hand because we're talking about current. Okay, then the motion is your thumb, so motion, and thumb has got an M in it, so that's why you use that one. And then your first finger is going to be the magnetic field, and your second finger is going to be your current. Now the really handy thing about fingers is that you can put all three of them at right angles to each other, just like my diagram here. Okay, so, and then what you need to do is, I mean, you can do this when you get into your exam if you want to, do it as long as it's not on the fingers before. Actually don't do that, because people might not know that you did it during the exam, so you might think you're cheating even though you're not. So motion field first finger, current second finger. motion, field, current. So first finger, second finger. And then what you've got to do is you've got to align that with whatever information you're given in the book. Now, in the question, sorry. So remember, your magnetic field always goes from north to south, and then you have to line it up with whatever information you're given. So you'll be given two of these, and you'll be asked which direction is the third one in. Now, you'll know it is at right angles, but will it be up or will it be down? Will it be left? Will it be right? Okay, and you can work that out. So for example, if I was to say that I've got a horseshoe magnet, and when I put a wire through it, my wire moves downwards if the current is in this direction here. So which one is my north pole and which one is my south pole? Well, so I line up my current. So I line up my current with this one. In physics exams, you'll see people moving their fingers around really weirdly. It's quite amusing if you know which question everyone's got up to. Okay, so your current's going that way. So it's going to move downwards. So that's your thumb, which means that your field must be going from here to here. Okay, so this is my north and this is my south. By lining my fingers up, I could work that out, and that agrees with this one because I changed my current direction and I also changed my motion direction, so therefore my poles must have stayed the same. Okay, those two effects will cancel each other out, so that's good. So have a practice with that because it's a little bit tricky to get your head around. But basically, all you're doing is rotating it around, but all your fingers are doing with Fleming's left-hand rule is just, it's a visual way of allowing you to know that you get motion is at right angles to the magnetic field, which is also at right angles to the current. And then, because we know from Newton's first law that if something is going from stationary to moving, then there must be a force acting on it. Well, we can work out what that force is, and the force is going to be equal to how strong the magnet is, which is B, which is magnetic flux density, because you don't care about how strong the magnet is, you care about how strong it is in per meter cube there. Okay, so you need to know how strong it is compared to how much space it's taking up. Okay. Times by the current. So how much current do you have going in that wire, which is the letter I, times by the length of the wire that is in the magnetic field, which makes sense. So basically what I'm saying is, how many field lines do we have here? How many field lines are we cutting through? What's the current in the wire? So how much current is there, and how long is the wire in the magnetic field? Okay, and you can see that handily spells out a nice little way for you to remember it. So the way to remember it is F equals Bill. That's the way you remember that. Okay, in the second half of this lesson I'll give you the example of the electric motor. There's a few little engineering feats that you need to know about as well for that, so it's not quite as straightforward as you'd think.